I have the pleasure to introduce you the NewCard project, which we have initiated in September in the last year, which is researching new materials for diesel reforming processes, and which is a cooperation in cooperation between Chalmers, where I'm from, PowerCell, Sandvik, and of course sponsored by Jan Kortort and Vinnova. And this is our consortium. Our projektstöd is Rakel Pettersson. Yes, so I want to tell you about the scope, the research plan, and the first steps along the way, since it's not initiated for so long now. So the scope is actually, it's a high-temperature corrosion project. For 1 year, I was part-time employed at PowerCell, and within the process of diesel reforming, we came across some optimization, which is only possible if we are looking at new materials. Then we started to discuss with Sandvik about more precisely Sandvik Heating, Kanthal. And we came across a new class of alumina forming alloys, which have very good heat transfer properties and supposedly very good oxidation resistance, and also chromium evaporation resistance, which is a big deal since you need to produce a lot of steam during the process, and you can volatilize chromium quite easily, which can cause problems downstream. So therefore it's very interesting for the project, and PowerCell is all in, and we in Chalmers, we have the capabilities to test these materials thoroughly before going into industrial testing. So therefore it's exactly what our research plan represents. We have the first material production in small scale, and we will calibrate the systems accordingly the new parameters given by PowerCell. And then we are, I should maybe say PowerCell is not only diesel reforming, it's of course a fuel cell company, a spin-off from Volvo, so which is looking into these hybrid technologies. That should have come earlier. As soon as we have our first experimental batches, then of course we go into laboratory testing first, and then we go into small-scale testing at the test rigs under real conditions, which are like 10 times harsher. So we're already testing in the laboratory on very harsh conditions. I think the harshest in the world for laboratory testing, but then industrial testing will be 10 times harsher even though. So not temperature-wise, but more flow and evaporation-wise. And so the first batch production was managed by Thomas and coordinated, so therefore I would give the word briefly to him.
Yes, and we are supplying the experimental materials here, and we will be looking at 3 different alloys. Stainless steel, austenitic 310 as a reference. We are looking at 2 different alumina formers, ferritic alloys. One which is commercially available now, and one which is a new material being developed. And as Christina mentioned, we will be looking at these in 2 different thicknesses. One rather thick, which is readily available, but for this project we had to supply thinner samples as well, 0.2 millimeter samples, and in order to produce this we had to turn to Sverige Mefos in Luleå, which helped us with cold rolling in their pilot facility. So right now we have cold rolled these materials down to 0.2 millimeter thickness, and as soon as they are ready with being annealed, we will supply them to Christina for further testing.
Yeah, thank you for this. I mean, it was an extremely good and fast solution to get these materials in for this project. Why are we doing this? Why 2 different thicknesses of the same material? What's the impact actually? So in Jülich, Germany, there was a study made which showed that if you look at 2 millimeter thick samples and compare it to maybe 0.1 millimeter samples under the same corrosion conditions, the behavior becomes much worse by a factor 2 or worse. So, which means you have like different effects. You are depleting an alloy much more rapidly from the corrosion protector. You are you have a different ratio from, so what is balancing which metal? So is the oxide scale supporting the metal, or is the metal supporting the oxide scale mechanically wise? So is it bending? Is it creeping? Is it stretching? Is it fatiguing? So all these has an impact from the sample thickness. And since we are looking at components which shall be rather thin, so we will make this comparison from the beginning. So this is one of the main focuses. And just rather quick, chromium reparation. How do you measure that actually? So you capture volatile species, which so-called denuded technique, which has been implemented at Chalmers for a long time and used for several theses. And now we're bringing that up to a new level since we are going very high in steam. So this is normally used for like 3% or 10% of steam, and now we're going up to 40% of steam, high flow. So really, we are testing this system on its limits. And so the sodium carbonate is reacting with the volatile chromia and captures that in a solid compound, which we can measure later on in quantitatively and online time resolved. So which is very good. So this was just a quick overview which I want to give you on this project and how we tackle these projects. Yes, and thank you for your attention.
Thank you very much. Ja, vi har tid för lite frågor till Thomas och Kristin. Är det någon som...
Yes, the commercial one will be alumina former will be Alcotal 14, which is a 15 chromium 4.5 aluminum alloy rest balanced on iron and some additions of reactive elements. And the model alloy, we have a first one which is only having chromium and aluminium, so no reactive elements and no other additions so far. So we are really starting from scratch there. But it's since we were a little bit uncertain about the rollability about these alloys, which is like a big deal. So if we can really roll it down to these dimensions, and 310 is our stainless, so one of the baseline metals which are used for so many applications, and it's like 60 years old. So there's sufficient data to compare with.
Okej. Tack så mycket. Tack.